Hello everyone, welcome back to Max Study. In this video I am discussing the topic reduction to diagonal form. So this is from linear algebra. We have a square matrix A of nth order. That means we have a matrix A n by n. Now we have to convert this matrix A to a diagonal matrix D. You know what is diagonal matrix? Diagonal matrix, the upper and lower portion, the lower triangular portion are 0. The only diagonal elements are non-zero. That is diagonal matrix. We have to convert the square matrix A to diagonal matrix, in which the diagonal elements are the eigenvalues of this matrix A n by n. That is we call the diagonalization or reduction to diagonal form. So the procedure is, first we have this matrix A n by n. We know that n by n matrix, nth order square matrix has n eigenvalues including the multiplicity. So first we find eigenvalues of this matrix, the given matrix A. Now we know that according to or corresponding to each eigenvalue, we have eigenvectors. Eigenvectors are the vectors x satisfying Ax is equal to lambda x, the non-zero vector x satisfying Ax is equal to lambda x or A minus lambda I x equal to 0. I am taking lambda x this side. So, A minus lambda I x is equal to 0. So, the eigenvectors are the vectors satisfying this equation. Okay. So, first find eigenvalues lambda i's, and corresponding to each eigenvalue find eigenvectors. That means we have linearly independent eigenvectors. So the square matrix A of order n has n linearly independent eigenvectors. Then only we can convert this to a diagonal matrix. So each corresponding to each eigenvalue we have n linearly independent eigenvectors xi's. Now this matrix, this is we called modal matrix. Modal matrix is the eigenvectors matrix. That means we got eigenvalues corresponding to each eigenvectors corresponding to each eigenvalue, and substitute or put it in the column. This is corresponding to the eigenvector x1 corresponding to lambda 1. And this is the eigenvector corresponding to lambda 2, and this is lambda 3, and etc. If it is a 3 by 3 matrix, we have lambda 1, lambda 2, lambda 3, 3 eigenvalues, and corresponding x1, x2, x3, 3 eigenvectors. So the modal matrix is of 3 by 3. So P is the matrix in which the columns are eigenvectors corresponding to the eigenvalues of the matrix A. So the diagonal matrix is P inverse AP. Now we find the matrix P inverse, and P inverse into AP is a diagonal matrix. This is the procedure. So not every matrix is diagonalizable. Only if a square matrix A of order n has linearly independent eigenvectors, then a matrix P can be found such as P inverse AP is a diagonal matrix. So every matrix cannot be diagonalizable. There are particular matrices which are not diagonalizable, which are not reducible to diagonalized form or diagonal form. Okay. Now let's do exercise 2.10. So problem 2.10. First question is, if a matrix A is given and a matrix P is given, show that P inverse AP is a diagonal matrix. So easy to calculate. We have to calculate the matrix inverse of this matrix P and finding the product P inverse A into P. Now we want to show that this matrix is a diagonal matrix. So let's do this problem. So the matrix A is given. A is given that minus 1 by 2, root 3 minus root 3 by 2 0, minus root 3 by 2 1 by 2 0 0 0 1. This is A, and the matrix P given as 1 by 2 root 3 by 2 0 minus root 3 by 2 1 by 2 0 0 0 1. So P is given as 1 by 2 root 3 by 2 0 minus this is minus root 3 by 2. That's root 3 by 2 1 by 2 this is root 3 by 2 and this is minus root 3 by 2 1 by 2 0 and 0 0 1. Matrix A is 0 0 0. Matrix A is 0 0 0. This is 0 0 1. Now let's find the matrix P inverse. Here we can easily find the inverse of this matrix P because this matrix P is orthogonal matrix. So the property of orthogonal matrix, you know what is orthogonal matrix? Orthogonal matrices are the matrices which satisfy A transpose equal to A transpose into A equal to identity. So the square matrix satisfying A into A transpose equal to A transpose A equal to identity. These are the matrices which are orthogonal, which we called orthogonal matrices. And the property of orthogonal matrices, its columns or rows, columns and rows form orthogonal or orthonormal basis. Orthonormal basis, or simply this is orthogonal vectors. The matrix orthogonal matrix satisfies its columns are orthogonal. So let's find columns and rows, both are orthogonal. Let's find these columns or rows are orthogonal. Let's take these two rows. What is orthogonal means? Orthogonal means the product. Dot product is 0. U dot V equal to 0. Let's find the dot product. This is 1 by 2 into minus 3 by 2. That is minus root 3 by 4. Plus this is root 3 by 2 into 1 by 2. That is root 3 by 4. Plus 0 into 0 is 0. So sum is 0. That is the dot product equal to 0 for these two vectors. And let's calculate for these two vectors. This is 0. This is 0. This is 0. So the sum is 0. And for 1 and 3, this is 0, 0, 0. Now taking the columns also, we get this dot product is equal to 0. That is, the given matrix is orthogonal matrix. So P is an orthogonal matrix. So now this is easy to find the inverse of an orthogonal matrix. That means orthogonal matrix always satisfies A into A transpose equal to A transpose A equal to identity. We know that what is inverse? A inverse is equal to identity, or A inverse A equal to identity. This is called inverse of the matrix A. Now look at this. Here A transpose is the inverse of the matrix A, since A transpose equal to identity and A transpose A also equal to identity. So A transpose equal to A inverse for orthogonal matrix. For an orthogonal matrix, A transpose is the inverse of the matrix. So to find P inverse, it's very easy. P is orthogonal matrix, so P inverse is P transpose. So P transpose equal to 1 by 2 root 3 by 2 0 minus root 3 by 2 1 by 2 0 0 0 1. So P inverse is there. Now we want to find P inverse A into P. So P inverse A into P. This is P inverse. This is A. Multiply P inverse into A. Then multiply it with the matrix P. So I am calculating this way. P inverse into A is there and this is P matrix. So what is P inverse into A? Matrix multiplication. First row, first column. This is minus 1 by 4 plus root 3 into root 3. 3 by 4. Minus 1 by 4 plus 3 by 4 is, this is 1 by 2. 2 by 4 we get, this is 1 by 2. Now this is minus root 3 by 4 plus root 3 by 4. So we get, not plus, this is minus. Minus root 3 by 4 minus root 3 by 4 plus 0. That means minus 2 root 3 by 4. That is minus root 3 by 2. And this is 0. Let's multiply this. This is matrix multiplication P inverse A. So again we get minus root 3 by 2 here and 1 by 2, minus 1 by 2 here and 0 here. And lastly 0, 0 and 0 here. 0, 0, 0. Yes, then multiply it with the P matrix. We get P matrix is this. Multiply with the P matrix, we get 1, 0, 0, 0, minus 1, 0, 0, 0, 0. So this is obviously diagonal matrix D. Now the second question, let's do this later, separate video. And now the third question, reduce the matrix A to the diagonal form. So we have given the matrix A as A equal to minus 19 and 16, sorry, 7, 16 minus 42. So this is the matrix A. To reduce this matrix to diagonal form, first we want to find the eigenvalues of this matrix. For that, eigenvalue is calculated using A minus lambda I, determinant of A minus lambda I equal to 0. We get the characteristic equation, and finding the root of the characteristic equation, we got eigenvalues. So first find A minus lambda I, determinant of A minus lambda I. So determinant of A minus lambda I, minus 19 minus lambda, 7 minus 42, 16 minus lambda. So the determinant is minus 19 minus lambda into 16 minus lambda minus 7 into minus 42. So we get minus 19 into 16 and plus lambda square. So lambda square I put here, lambda square, and minus 19 lambda minus 16 plus 16 lambda. Sorry, plus 19 lambda minus 16 lambda is 3 lambda, and here minus 42 minus 42. So 42 into 7 is, and minus 19 into 16. We got the number minus 10. So after calculating, we get the characteristic equation lambda square plus 3 lambda minus 10. So this is the characteristic equation of this matrix. Let's find characteristic roots or roots of this equation. that is eigenvalues. We can write this equation as lambda plus 5 into lambda minus 2, that is lambda square plus 3 lambda minus 10. So substituting the determinant equal to 0 means lambda plus 5 into lambda minus 2 equal to 0, that is the roots is lambda equal to minus 5 and 2. So these are eigenvalues. Lambda 1 is equal to minus 5 and lambda 2 is equal to 2 are eigenvalues of this matrix A. So we found eigenvalues A, lambda 1 and lambda 2. Now we want to find eigenvectors corresponding to these eigenvalues. Now let's find the eigenvector corresponding to the eigenvalue lambda 1 is equal to minus 5. So A minus 5y, that means A plus 5y into x is equal to 0. That is the matrix A plus 5y, minus 19 plus 5, minus 19 plus 5, minus 14, and 7 is 7, and here minus 42, and 16 plus 5, 21. Now x is x1, x2, let it be x1 and x2, and 0, 0. So minus 14 x1 plus 7 x2 equal to 0, first equation, minus 42 x1 plus 21 x2 equal to 0. These are both are similar equation. When divided by 2, we get minus 2 x1 plus divided by 7, minus 2 x1 plus x2 equal to 0. And divided by 21, we get the same equation, minus 2 x1 plus x2 equal to 0. So x2 equal to 2 x1. Now we put x1 equal to 1. If we put x1 equal to 1, we get x2 equal to 2. So the eigenvector corresponding to the eigenvalue lambda 1 is 1, 2. Okay. Now let's find eigenvector corresponding to lambda 2 is equal to 2. So A minus 2i into x equal to 0. A minus 2i, the matrix is minus 19, minus 2, minus 21, 7, minus 42, 21, minus 2, 19. Sorry, 21 plus 16. It's 16. 16 minus 2, it's 14. Okay, x1, x2 equal to 0, 0. So minus 21 x1 plus 7 x2 equal to 0. Minus 42 x1 plus 14 x2 equal to 0. Now this is divided by 21. We got minus x1, sorry, minus 7 divided by 7, minus 3 x1 plus x2 equal to 0. Same, divided by 14. Yes, we get the minus 3x1 plus x2 equal to 0. So x2 is equal to 3x1. That is, if we put x1 equal to 1, then we get x2 equal to 3. So the eigenvector corresponding to second eigenvalue is 1, 3. Okay. So the modal matrix P equal to 1, 2, taking first eigenvector as first column and this as second column. Now let's find the inverse. P inverse. P equal to 1, 2, 1, 3. P inverse. What is determinant of P? Determinant of P is 3 minus 2, 1. Determinant not equal to 0. So inverse exists. So inverse of a 2 by 2 matrix is 1 by determinant of P into adjoint of A. What is adjoint of a 2 by 2 matrix? This is reversing this elements and negative to this one. So the P inverse is 3 minus 1 minus 2 1. You know the inverse of a 2 by 2 matrix. Reversing the elements of diagonal and putting minus 2 of diagonal elements. We get adjoint. So P inverse is 1 by determinant is 1. 1 by 1 is 1. So P inverse is 3 minus 1 minus 2 1. Now let's find P inverse into A into P. P inverse into A minus 19 7 minus 42 16 and P is 1 2 1 3. Let's multiply first second. This gives 3 minus 19 plus 42. We get minus 15 and 21 minus 16 5 and 19 into 2 38 minus 42 is minus 4 and minus 14 plus 16 is 2. Now this is 1 2 1 3. We get the matrix minus 15 plus 10 is minus 5, minus 15 plus 15 is 0, minus 4 plus 4 is 0, minus 4 plus 6 is 2. So this is our diagonal matrix D. So P inverse AP is a diagonal matrix D. So we reduce the matrix A to diagonal form in which the diagonal entries are the eigenvalues of the matrix. Minus 5 and 2 are eigenvalues of A. So this is the diagonal form of the matrix A. Okay, I hope this is clear to you. Please subscribe and share this video to your friends. I upload the remaining questions in the next video. Thank you.